and he's currently the program manager at the NASA headquarters. His research area are quite mentioned here, but I'd like to mention about his certificate, his educational background. He's the PhD in atmospheric chemistry, Georgia Institute of Technology. He has been very busy, but very kind to take out the time out of his busy schedule and speak us, share his invaluable insight with us today. So, Dr. James, thank you so much for joining, and I'll hand over the stage to you. I'll stop sharing the recording and you can share your screen if you have want to share any slides.
Okay, I appreciate the introduction, and I appreciate the invitation from Fahim to participate today. He and I have been interacting over the past year quite a bit on air quality issues and see a lot of real potential for progress in Pakistan to try to understand air quality better, as we need to do around the world. And so, my time at NASA has really been spent doing airborne science, and so you'll find that what I decided to do today is do a presentation for you that's very heavily weighted towards airborne science. This kind of capability is not really available very often around the world, and so it's good to have a chance to see what you can learn from that. And so the title of my presentation is Improving Understanding of Air Quality Through Integrated Observations and Modeling, and this little graphic I provide down here in the corner kind of tries to present to you that a complete understanding of air quality requires multiple perspectives in terms of observations. It's really on the ground that you get the best information about what local air quality looks like and what exposure is. But as I'm going to show, you can only do this in so many locations. Satellite observations provide an opportunity to look globally at what's happening with respect to air quality. But I would argue that satellite view is also not sufficient by itself. And trying to find a way to understand what a satellite sees and its relevance to what's happening to you down at ground level requires a lot of investigation. And so there are opportunities to fly research aircraft in ways that can help understand the connection between these two ways of viewing things. While these two things happen with continuity over time, the aircraft can only be done for short periods of time. But ultimately, all the information that we can gather observationally has to improve our ability to both forecast and understand air quality through models. And only through models can we really develop an understanding of what changes need to be made to improve air quality. And so to move beyond simply understanding that air quality is poor in certain locations to moving towards decision making really takes place in this modeling realm. I want to start by giving you a view of what ground level air quality monitoring looks like on a global scale. This website at AQICN is one of the few places where you can go and get up-to-date information on air quality at many locations. This really represents the extent of information that's at our fingertips. And so, you can go to this website and see what air quality monitoring is happening closest to you. There's a lot of activity here. It's quite encouraging to see how much air quality is being measured around the world. But it's important to understand that, the quality of air of monitoring is happening at any given location varies quite a bit. One other resource is the OpenAQ website, which again has a very similar landscape of information. Here you're looking at data for PM 2.5, but you'll also notice that low-cost sensors are contributing more and more to the landscape of observations. And again, density of low-cost sensors is important because the quality of those measurements is not quite so good. And I also want to emphasize that it's important that we not only measure the things that are affecting our health, like PM 2.5 and ozone, which were discussed earlier, but we really need to understand the precursors. What are the mixtures of things that are leading to the PM 2.5 and the ozone? Because those are coming secondhand in the atmosphere. You don't put ozone directly into the atmosphere. It happens chemically from all the other things that we're emitting from our activities across the globe. Now, as encouraging as this is, if you were to go to that AQICN website and zoom in, now you really begin to see that there are large portions of the globe that really have no monitoring. I've highlighted your part of the world, and you can see that, Pakistan has a few monitors, but there's many areas where you really don't have quality information in terms of what's happening in real time. This leads to the desire for satellite observations. And so you begin to immediately appreciate the idea that, well, if I had satellite observations, I could begin to understand maybe what's going on in all of these gaps in terms of what's happening with emissions and air quality in certain parts of the world that are under monitored. And that's the lure of satellite observation. So I want to highlight a group of satellites that has been, coming about really over the past decade. And so, air quality observations from space are really coming into their maturity. We've been measuring certain things from space for about 20 years now, but this is the first time in which we'll have what begins to approach sort of a global view of air quality with some level of continuity. You see 3 satellites that are in geostationary orbit. So these 3 satellites, one for the United States called Tempo, one from Europe called Sentinel-4, and one for Asia called GEMS, are at geostationary orbit and can look at things with continuity. So all day long they can stare at what you can see here as the 3 major economic zones in the Northern Hemisphere that deserve the most attention. What you're looking at in terms of the color map is a distribution of nitrogen dioxide. And I'm going to highlight NO2 today. It's just one component of many things that Fahim would have talked about earlier in terms of pollutants, but it's the one that we measure best from space. And it's also the one that really highlights human activity because it's related to combustion activities. And so through high temperature combustion in power generation or transportation or industry or even fires, NO2 is generated in the atmosphere. Another very natural combustion process is lightning, which also creates NO2 in the atmosphere. But the real use of NO2 is that it's very short-lived. And so what you can see here very clearly are major cities and domains where humans live and breathe. And so NO2 is the best satellite product for really pinpointing where populations are exposed to poor air quality. These other satellites that you see below are what we call low Earth orbiting satellites, and they each can provide observations at a global scale, but only one time per day. And given the way that daily air quality dynamics play out, it's believed that that one time per day is not sufficient to really understand what's happening with air quality. And so that's why we have moved to this geostationary view, where we can look hourly at what's happening from morning until evening, with morning being when activity begins to really pick up during the day, and evening being when the chemistry of air quality can lead to some of the worst conditions in terms of exposure to ozone, particulate matter, and other damaging things. And so this satellite view becomes a very compelling opportunity to really capture what's happening globally in terms of air quality. However, it's important to understand that really understanding what's happening near the surface is very difficult for making observations from space. And so I want to take you through some of the challenges in interpreting what a satellite is really seeing. Near surface information must be inferred from column integrated quantities. And so this white line here reminds you that the satellite's really looking down through the atmosphere. So sunlight penetrates the atmosphere and then reflects back to the satellite. And so the satellite sees the sum total, or the total amount of the impact of a given molecule that it's trying to detect, or particle that it's detecting through the whole atmosphere. And so it's very difficult for the satellite to tell you where in the atmosphere vertically the pollution is distributed. And some of those constituents, you've already heard about ozone, but also NO2, can have large abundances in the stratosphere. And so you have to account for that stratospheric burden. This is much more difficult for ozone, but for NO2, it is quite standard to deal with that because it doesn't dominate in the polluted areas. But you still have to understand that there's NO2 and ozone and other things in this stratospheric layer. You can also have long-range transport of pollution at higher altitudes. You can see this very easily in maps of carbon monoxide, but also For instance, a power plant plume that contains high aerosols and NO2 will show up very strongly in a satellite image, but may not be down at the surface where you're being influenced, but coming overhead. But it will still be part of the total amount that a satellite would measure from space. When looking from space, the size of the measurement pixel is important to understand. So there can be very fine gradients in pollution that you need to be able to see very high spatial resolution. This also matters for models because the chemistry that takes place in terms of air quality outcomes, is very nonlinear. And so if you don't capture the right gradients, it's very difficult to really predict what's going to happen with air quality conditions as the day progresses. The final piece that's really important to understand is how the boundary layer depth influences the volume over which surface pollution is mixed. And so you can understand that early in the morning, the boundary layer is very shallow. Pollution being emitted into the atmosphere is contained in a very small volume, and that can allow it to build up to very high concentrations. As the day goes and the ground heats up and the air begins to mix vertically, you can often ventilate or dilute the pollution that's down near the surface. But this same dilution process can actually be something that makes the chemistry outcomes, for instance, ozone production, can actually accelerate due to that dilution of the pollutants into a regime where the chemistry goes much faster. And so how well the pollution is mixed really does matter in terms of what's going to happen as the day goes on. It's also important to add a few more things in terms of other factors. Relative humidity is very important, especially for particulate matter. What we measure on the ground for your exposure to particulate matter is a dry mass or weight of aerosol. We bring it into the instrument, we dry the airstream, and we physically measure how heavy the weight is of the particulate matter in the air. But when you measure from space, that particulate matter is often very sensitive to humidity. And so when it's very humid, the particles can take on water vapor and swell in size, and that affects the way they scatter light back to space. And so the amount of particulate matter that you might infer from a satellite is very sensitive to understanding the humidity conditions. And so in a dry atmosphere versus a wet atmosphere, the same amount of particulate matter can cause the satellite to see something very different from space. And that's really what I want to talk about today, is trying to understand better what the spaceborne view versus the ground level view looks like, how they compare, and an appreciation for what those two views add to our understanding of what's happening with air quality in any given location. My work on this began back in 2011 with a series of field campaigns that NASA was willing to fund, and the name of the campaign was Discover AQ. It stands for Deriving Information on Surface Conditions from Column and Vertically Resolved Observations Relevant to Air Quality. It's a very literal acronym that talks to the procedure that we were using to understand things. And so if you look at the graphics for each of these locations that we visited in the US, you see a red line with these sort of little spiral symbols. And so we flew an in-situ sampling aircraft. So we were measuring air composition directly along a path that took us over 6 air quality monitoring sites in each location. And we would profile the atmosphere in terms of composition above that monitoring site, in terms of what the atmosphere looked like in terms of vertical structure or a sounding of air quality over the site. A second aircraft flew high overhead with a remote sensor, which is trying to replicate what a satellite would see, a total column amount rather than the detailed vertical structure that is present in the atmosphere. We also had ground-based remote sensing, and a very important part of this talk has to do with the Pandora spectrometer. While we didn't have geostationary satellites at this time, we did want to have observations of total column amounts throughout the day. And so the Pandora spectrometer looks at the sun, and the light that passes through the atmosphere to the spectrometer can allow it to detect the total column amount of NO2. Now it can detect other things. You can detect ozone, formaldehyde, aerosol optical depth. But instead of going broad for this talk, I'm going to focus in specifically on NO2, particularly because we can measure it with very high precision. And it really highlights these questions of what does a satellite see and why is it different than what you would see from an air quality monitoring instrument on the ground. And so I'm going to go through a series of observations from these campaigns to show the different views, the view from the Pandora spectrometer, the view from the ground monitor, and the view from the vertical measurements from the aircraft. Before I do that, I want to talk a little bit about how models were predicting NO2 column behavior just before these campaigns began. And this is a very famous figure from Jack Fishman's paper in a 2008 paper in BAMS. And what he was showing here is the modeled column NO2 amount, which is this dark blue line. He was showing the surface NO2 amount, which is this pink line. And he was also highlighting the time of day that current low Earth orbiting satellites were observing NO2. And you see several things here. I've highlighted the daytime periods in yellow because that's when the satellite is actually able to observe. It's based on, detecting the reflection of UV light back to space. And so in the morning, you see both the column and surface amounts increase. And this is because of both the shallow boundary layer in the beginning of the day where a lot of human activity is beginning. And as these things increase, you see that the surface values begin to decrease at an earlier point in the day. The reason the surface values begin to decrease is because that boundary layer is growing. You're diluting what's at the surface and you're distributing the pollution over a larger volume. But from space, you're seeing the total column. So that change in volume does not change what you see from space. You see this continuous increase as emissions begin to grow. And so the total emissions are better seen from space in terms of the total column. Due to chemistry and transport and other dynamical considerations, I mentioned the short lifetime of NO2. You see in the afternoon, things begin to precipitously drop. This is during the period of greatest ozone formation. And then you see that NO2 observed from space by a low Earth orbiting satellite is really happening at the time of day that seems least useful in terms of understanding how much emissions are occurring. And so it was this view that really drove our understanding of why we needed to make geostationary measurements from space and why we proposed to do some field studies that will try to understand how this plays out in real time with real data, not just a model predicting it. A second model study was also published during this time, and it was looking with Skiamaki data and trying to understand in terms of the actual processes, what drives that change during the day. So let me just go back real quick to the previous slide. I want to mention that you're looking at from morning to afternoon, changes in NO2 column that are on factors of 2 to 4. So you're seeing these decreases in column NO2 by amounts of 2 to 4 times. This model also predicted decreases during the day of the NO2 column by factors of roughly 2 between morning and afternoon. And you see that's due to several factors. One is the partitioning of NO2 as part of NOx, which may have been mentioned earlier in terms of the photolysis of NO2 and the reaction of NO with ozone. So that balance between NO and NO2 begins to favor NO during the day. And so you see less NO2. You also see that the emissions increase during the day, but more importantly, the photochemical loss or the chemical degradation of NO2 is maximized again during the day at midday, that time when you see going back to the previous figure. So again, midday is when you see this large drop in NO2. That's presumably because that's when you have the largest rate of photochemical loss of NO2. So from a model perspective, these two studies were very similar in their view of how NO2 would behave in a space or satellite measurement. When we went and made measurements in the field with the Pandora spectrometers, now I'm showing you the diurnal trend in NO2 measured across the Maryland domain from the Pandora spectrometer. So think of this as the diurnal trend in column NO2. And what you see here is it looks nothing like what the models predicted. There's no factor of 2 to 4 decrease in NO2 between these morning hours and these afternoon hours. And so the question became, what really is going on here? Why do we not see what the models would have predicted? One thing I want to emphasize here is, first of all, you see the green values always tend to be low. That's the remote site. The blue values always tend to be high. That's the most polluted site. And so the Pandora spectrometers do show you that there is a very strong spatial gradient in NO2 across the area that's being sampled. But during different times of day, that gradient doesn't seem to change very much. And this was something that was very unexpected in what we had measured. In terms of talking to the modelers, they basically didn't understand what was happening here and really challenged us in terms of whether these measurements were correct or not. And that's something that always is important to realize, is that measurements and models are imperfect. And so both measurements and models need to be scrutinized when they behave in ways that maybe don't make sense to what our preconceived notions are of what we expect to see. And so the real value of this campaign was that not only did we measure NO2 column over time, we also had an aircraft profiling above these locations. And very quickly, though, I want to remind you there's a stratospheric burden of ozone, and this dashed line represents what the stratospheric NO2 component would be. And so there's not a lot of variation in stratospheric NO2. And so when you subtract that number off, you still see there's no evidence for the lower atmospheric NO2 to change very much with time of day. What you do see, however, is that when you take the profiling of the aircraft, and this was done over a month's time, so these statistics represent a month or 10 different flight days of profiling all through the day over these sites, you see a very interesting situation taking place. And so in the early morning, 6 to 9 a.m., as we mentioned, all the NO2 is down very low. And this point represents the lowest altitude that the plane can fly. And the dashed line connects you to what the ground monitors were seeing. So this is off scale. This is out at 7 ppb. And so early in the morning, all the NO2 is very low in the atmosphere. And as you move to the red curve, which is 9 to 12, and then 12 to 3 p.m., and then finally 3 to 6 p.m., what you begin to see is, again, this idea that things are mixing deeper and deeper into the atmosphere. There are two things to recognize here that go against conventional wisdom. The first is that people tend to consider the boundary layer to be well mixed. The time constant for mixing things in the boundary layer is about an hour. And so you would think that most constituents would have fairly flat gradients in the boundary layer, something more vertical like this. But the thing you also have to realize is that the emissions of NO2 are continuing in time. And so you always have the highest values near the surface, and you are mixing more and more of that material up into the atmosphere throughout the day. And so the flat column that you see in the previous slide is really coming from a balance between the chemical loss and the emissions that are being mixed deeper and deeper into the atmosphere. And so this became, a very different way of looking at what you would see from space versus what you see on the ground. The same thing was seen when we visited Houston. Again, Galveston, which was the most remote site, always had the lowest NO2. And then West Houston, which was the more polluted site, had the higher NO2. But again, very small changes throughout the day, nothing that would represent a factor of 2 change that the models were predicting. And so this became a very important multi-perspective view on how things were taking place. It wasn't until we went to California that we actually began to see changes throughout the day in the column of NO2 that actually began to look different than those sort of very flat diurnal profiles that I showed you for the first 2 sites. In this case, I want to remind you, though, that the models all predicted that NO2 would go down by factors of 2 to 4. In California, at least 2 of the sites, NO2 is actually going up by factors of 2 to 4. So again, we're beginning to see some movement, but not in any way that would have been predicted by the model viewpoint that preceded the work that we're doing here. Now, in this case, 2 sites are moving up and the other sites are staying flat. And this is something that again, we need to ask ourselves, does the aircraft corroborate that? And it does. If you isolate what's happening in terms of the profiles for the 3 times of day, morning, midday, and afternoon, for the 2 sites that were going up, this is just for Bakersfield and Fresno, you see that, again, in the morning, things are very low, and then they build up during the day. But what you don't see here that you saw in Maryland is you don't see a dilution of NO2 down near the ground. You see that the NO2 remains very high. And so in this sense, we're in a wintertime study in an area that has 2 cities and then a rural surrounding. And so in the stagnant conditions, what you're finding is that the polluted air doesn't make its way out into the rural areas. And in the polluted areas, it builds up throughout the day into that deeper mixed boundary layer. And so again, having these aircraft measurements profiling the atmosphere overhead provides statistics to explain or corroborate why here you see increasing column amounts, but the surface values do not get diluted. So that's a different view than we had seen in the previous two sites. Moving to Colorado, I want to try to bring together for you a better picture of what the value is for the standpoint of what a satellite sees versus what the ground sees, and how the aircraft helps interpret that. When we got to Colorado, we had this one site called La Casa. It's in the city of Denver. And to be honest, when we first saw this, we again wondered if this could be correct. Fortunately, we had a second Pandora site in the city that was along the roadway, the I-25 roadway, and that's in black. And you can see that the two urban sites had very, very different amounts of NO2 than the surrounding areas, which again shows you that you can have very high concentrations of NO2 in one location, and not far away, things can be much cleaner. To describe what's going on with these measurements, I want to go back to sort of a satellite type view. And so geographically, we're in Colorado. This is the city of Denver. You can see the roadway that circles the city, and then the other highways that lead in and out of Denver. To the west, you have the Rocky Mountains. And so this entire domain that's populated is nestled in the foothills of the Rocky Mountains. So a very strong mountain circulation is driven in this area. And so what you're seeing here in white is the path that the P3 was flying. And so the circles you see are where it's doing those spiral soundings over the air quality sites. And what you're seeing is also the map that was taken from the high-flying remote sensing aircraft. And so it's mapping NO2 once in the morning and once in the afternoon. And you can see that there's this one hot spot just to the northeast of Denver where most of the NO2 is coming from. But in the surroundings, you also see something else that's very different. So in the morning, that hot spot seems to be feeding higher NO2 levels that are off to the northeast. That's because the Platte River Valley leads out in this direction. And so during the nighttime, airflows come down the mountain and down that river valley and sort of push that NO2 out away from the mountain. And during the day, when the boundary layer heats up, the air moves back towards the mountains, and you begin to see that NO2 moving back towards the foothills of the Rocky Mountains. And so this is corroborated by a lot of the P3 measurements, which here again are shown by the amount of NO2, by the latitude that we were flying. And you can see that again, the highest values are at this same latitude of where we see the high NO2. And even more interestingly, when we move up into this region up to the north, you can see that the smaller symbol sizes, which indicate data taken further away from the mountains, have the higher NO2, and that correlates to the morning push of NO2 away from the mountains down the Platte River Valley. Now, taking this view back to the column and surface, let me just go back real quick. I'm going to take three sites. I'm going to take the Golden site, which is near the mountains. I'm going to take the La Casa site, which is out here in the city, and then that I-25 site, which is along the roadway in the city, and try to contrast for you what the satellite view is, which is really the Pandora view in this case, and what the ground view is. So the column densities are read off of the left scale, and you have three curves. You have the purple curve, which is the La Casa site, which is the city site. You have the black curve, which is the roadway site, and then you have the green curve, which is the one that's in the foothills of the mountains. And what you see here is that those values have their greatest difference in the morning, and throughout the day, the green curve tends to grow and grow and not really become as high as the urban values, but it begins to approach the urban values. So the difference between the foothills and the urban setting are much smaller in the afternoon than they are in the morning. And that corroborates what we saw in the previous image, where by the afternoon time, you've pushed a lot of NO2 towards the mountains. Now, if we look at the lines, which is the average condition that's read off of the right-hand scale for the surface NO2, you see some more interesting information. First of all, at the La Casa site, you see that the NO2 decreases very rapidly in the morning hours while the column is increasing. And so the column is going up by about a factor of 2. And the surface value is going down by a factor of 2. So the relative change between what you would see at ground level and what you would see from space is a factor of 4. That's a really large difference. But remember, what you're seeing at the ground is related to what people are being exposed to, and what you're seeing from space is the total amount of emissions. And so without the spaceborne view, you really don't understand that there's a lot of NO2 being emitted during this period is simply being ventilated to higher altitudes. The other thing that you see is that the decrease in the black line is much less than the decrease at La Casa, and that's because this is along a roadway. And so again, the dilution of emissions has a lot to do with its proximity to the source of NO2. And so the NO2 is driven down at the surface in very different ways compared to what you see in the column, which is much more similar. And then finally, in the green line, what you see is that even though in the column, the increase in NO2 in the foothills has created this increase, there's no evidence of that down at the surface. And so by just measuring at the ground level, you don't recognize this important transport feature of where the pollution is being transported in that location. And so this begins to help you understand the value of those observations, each providing different information, but valuable information on what's happening with emissions of NO2. I just finished by showing you the profiles from the La Casa site. And there again, you see in the morning, everything's packed down low, but the difference between this blue and this red line is really, really strong. And so what you're seeing is that, at the ground, you see things decreasing very, very strongly, and a lot of the NO2 is out of view at altitude. And this really matters for a number of things, because recognize that the ozone formation is taking place across this entire volume, and the boundary layer mixing is helping distribute that ozone. And so if you tried to calculate ozone production based on this purple line, you would come up with a very different answer in terms of calculating ozone production based on this column line. And so this really begins to show the value of how satellite data can help in this regard. Let me move on to another example from Korea. So we took this experiment to Seoul, Korea in 2016, and this was mainly because the GEMS satellite, which is already launched over Asia, was another satellite region that we wanted to understand better. We wanted to work with our Korean colleagues, and so we did a similar sampling regime over the city of Seoul. And the Olympic Park Research Site was the major location that we did aircraft profiling over. We begin with, again, the surface and Pandora observations. And I would emphasize once again, in terms of the column NO2, we see yet another pattern, a different pattern than what we saw before. We also see much greater column densities. If you looked at what we saw earlier, column densities were typically down here in the 0.5 to 0.8 range, and now we're moving up into the 1.5 to 2 Dodson units of NO2. These are really polluted conditions. But again, you can see that the trend is not down in the afternoon, as models were suggesting 10 years ago. It's actually up in the afternoon, and that's because of the accumulation of emissions as the day goes on. But even in Korea, the mixing and dilution is enough to create a situation on the ground where you see the morning rush hour where activity begins and the NO2 is up and accumulating in that shallow boundary layer. But as the boundary layer ventilates, the ground perspective really loses track of what's happening in terms of total NO2 emissions. Aircraft profiles of NO2 over the same site show a very similar picture that I'm showing you from the other locations. And so what we do understand in models is that, material is very contained in the early morning here below 500 meters. And then as the day goes on, things are mixed to higher altitudes, which dilutes what's at the surface, but can lead to higher column densities. And so in terms of understanding how local boundary layer dynamics takes place, that really is a key factor that needs to be understood if you really want to relate what a satellite is seeing versus what may be happening with ground monitors at nose level. While I've focused on NO2 almost exclusively during this talk, I want to remind you that there are many other important molecules that are being observed from space, and they're relevant to both the production of ozone and fine particle pollution. So here the NO2 and formaldehyde represent the NOx and VOC combination that leads to ozone formation, but also recognize that nitrate aerosol is very much affected by the high NO2 levels in Seoul, and formaldehyde indicates the oxidation of hydrocarbons, which lead to a very large organic aerosol component in that domain. And so while it's important to look at ozone and PM 2.5 directly, you really begin to understand their origin by looking at the precursor compounds that lead to the outcomes in terms of high levels of ozone and fine particles. The thing I really want you to notice here, though, is that the vertical distribution of NO2 and formaldehyde look very, very different. And this has some implications for how we try to understand air quality. First of all, we ask the question, why does formaldehyde look so different in the vertical dimension? And it's because it's not an emission directly. NO2 is emitted from tailpipes, it's emitted from industries, it's emitted from power plants, it's emitted from many, many different sources. Formaldehyde is the outcome of the breakdown of hydrocarbons. Those hydrocarbons, again, come from fossil fuel usage, they come from industry, they also come from solvent usage and natural sources. Trees and vegetation also contribute a large amount of hydrocarbons into the atmosphere. And so instead of seeing the mixing of formaldehyde, what we're really seeing is the creation of formaldehyde. And so as the boundary layer deepens throughout the day, you simply have a larger volume over which the hydrocarbons are distributed and a larger volume over which chemistry can act to break them down and generate formaldehyde. So what you begin to see is that the intersection between these two molecules that work together to create ozone differs with altitude. And that means that the rates of ozone formation will differ with altitude, and that our understanding of ozone formation rates from ground level will be skewed versus what's really happening in the total overlying atmosphere just above your head. So that's really what I wanted to take you through today. And I have some key takeaway points. And so from all that I've talked about, what I really hope that you can see is that satellites are playing a key role in expanding access to air quality information. Without them, there are many areas we really wouldn't understand. But I want to emphasize that continued proliferation of ground monitors is essential. Without the ground monitor, we're really not going to be able to understand completely what's happening with air quality in any given location. And so, especially in South Asia and that part of the world, we believe that ground monitors are a very important priority, and we hope to see more of that happening. Second, there's a broad diversity in surface to column behavior that results from the interaction between emission strength, boundary layer dynamics, and chemistry. And so as I took you through each of these locations that we have visited, you see in each location what we saw in the Pandora spectrometer column measurements and what we saw from the ground measurements really differed quite a bit. And it was mainly in the column that we saw the biggest change from place to place. And so using Pandora spectrometers can be a great way to locate in a domain your ground measurement to understand how the boundary layer may be behaving. And then aircraft measurements, when available, can really help us understand how to test models in that regard. The next thing I want to emphasize is that, satellites see column abundances, and those column abundances really provide a superior view of total emissions. How much stuff is making it into the atmosphere? It's very important that models have accurate emissions, because if you're not putting the right amount of material into the atmosphere, it's very difficult to really strategize an understanding of what's causing poor air quality and what emissions should be controlled to improve air quality. And so that's really where I think the satellites come in as the most important contribution, is in their ability to assess emissions. But ground measurements are necessary for quantifying pollution exposure. Any attempt to really protect you has to do with what you're breathing at ground level. And the satellite doesn't see that quite as well. So the ground measurements really become the key aspect of this integrated system that I began to talk with, in terms of combining satellite observations, ground measurements, and models with aircraft observations in locations and times where they're available, to really try to understand better what's happening and paint a complete picture of what's happening with air quality. And so I'm not sure how long I took, but with that, I'm happy to stop and take questions and maybe add some more details if you have questions about other pollutants and things like that. So thank you.
Thank you, Jim, for this very interesting talk. Definitely. So there will be a couple of questions, I guess. So audience, please raise your hand and ask your question, and then wait for the response. So we have first question from Dr. Asif Khan. Please go ahead.
Yes, so thank you very much, Dr. Fahim. Thank you, James, for such a wonderful presentation. I was looking at data, and you did a wonderful comparison between the in your first study. So I was wondering where you talk about the more level of variation in NO2 in the state of California as compared to Maryland, for example. What do you think could be the cause for that increased variation in California as compared to Maryland? Thank you.
Yeah, so that's a good question. So the Maryland was a summertime study. And summertime studies bring two things. It brings more vigorous dynamics and it brings more chemistry. And so what we were seeing in Maryland is that the mixing and loss of NO2 was balancing out. So the rate at which we were emitting NO2 was balanced with the rate of chemical loss. And so as the column was, as things were being ventilated, the column didn't change, but what you saw at the surface was being diluted more and more as the day went on, but the total amount really didn't change very much. In California, it was wintertime. And in wintertime, there's a longer lifetime of NO2, and there was very cold, stagnant conditions. So the NO2 was being contained very near the source. And so the two locations, which were cities where the NO2 was being generated, you were building up throughout the day very large concentrations. And the outlying farming areas were essentially free of NO2 because the transport was very, very slow. And so, again, the dynamical situation can be very, very important to understanding what's happening in each location.
Okay, wonderful. Thank you very much for that.
Yes.
Dr. Asif, any other question from the audience? Yes, we do have Mohammed. I can't see your name exactly. It's Mohammed Hassan. Can you please go ahead?
Thank you so much, Professor, for such a wonderful presentation. The question I had was relating to you talked about the how we measure the emissions from satellite, right? So the thing that I understood, if I'm incorrect, please correct me, that the satellites are in a geostationary orbit and they look at a specific column on the land, and they take the data, but that's only part of the data. Then you correlate it with land data that is available at monitors. So my question is, so this appears to be a very comprehensive and detail-oriented system that requires a lot of experts like you. How can, in a country like Pakistan, with the resources we have, how can we, employ a system of monitoring that uses all these techniques and tables, but is more manageable in our concern, so that we have the data to, take necessary actions for the well-being of our countrymen? Thank you so much, Professor.
So, the satellite view is available everywhere. And so the question becomes, how do you take advantage of that satellite view to learn more? And so until you have the ground site, at least one, I would argue that one very comprehensive ground site in Pakistan could be very, very useful, because now you add this idea of how did the ground NO2 change and how did the column NO2 change? From that, you can begin to try to infer what's happening with boundary layer mixing and other things. But you also, things like salometers, which would show you the boundary layer depth with time. Those are very inexpensive. I don't think aircraft observations are needed per se, but on the ground, if you could measure NO2 with high precision, maybe have a Pandora spectrometer and a salometer, I think you could tease apart many of these details quite easily. And as you saw in a place like Maryland, we had 6 Pandoras located in Maryland, but diurnally they all had the same trend, right? And so very often you'll see that you don't need a lot of ground sites to connect to space. You need at least one comprehensive site. Then as you build other ground sites, they don't need to be as rigorous. They can begin to help with the spatial distribution. So let me go back. I'm trying to watch my camera here and my screen at the same time, so I'm going to move the camera to the side. And let me go back to the Maryland situation just real quickly. So what I really like about what we're seeing in Maryland is that the satellite is going to be able to give you the spatial distribution of NO2. You'll be able to know where the polluted areas are and where the, where the clean areas are. But if you just had one Pandora site in this region, would be enough to understand what's happening diurnally in terms of the column density and boundary layer. I want to emphasize one other thing I didn't have in the talk, and that's that, a satellite retrieval is actually more complicated than a Pandora observation. Pandora observations are based on the sunlight coming all the way through the atmosphere to the detector. Fahim knows a lot about max DOAS, so he can explain this to you guys as well, is that, we know that the photon that came to the Pandora made it all the way through the atmosphere. But from space, the light is scattered back, and that light scatters back from different altitudes, and aerosols in the atmosphere may make sensitivity less towards the surface. And so the satellite view is an optimization retrieval. And so it's not as accurate as the Pandora. So the other reason to have a Pandora site in Pakistan is to determine whether local particulate matter is interfering with the satellite retrieval. And I don't have enough in this talk to go into that, but that's a topic that that you might pursue with Fahim and understanding how a Pandora could be useful in Pakistan. So probably more than you wanted to hear, but those are some aspects of what I think could be very useful for you in the local study of air quality.
Okay, let's have another question from Kainat Javed, please.
Yes, thank you so much, Mr. James, for your insights. I want to ask about, as we have seen that the satellite images have played a vital role in determining and specifically creating awareness in a layman regarding the atmospheric changes. So how do you see that, what is the future of GIT with respect to air quality specifically, as you have mentioned to the response of Hassan Dajana, that the things may vary because we cannot completely rely on it because the light's altitude vary and angles vary. So what do you see GIT in future with respect to certain air pollutants in air quality? And do you think that these technological specialization can bring change in the policy, global policy? Thank you.
Am I still sharing my screen?
No.
Not you. You have to reshare, Jen.
Okay. Let me do that. I want to go back to the satellite view. And when you say GID, what do you mean by that?
Oh, it's like geographic information technologies.
Ah, okay, okay, very good. Yeah, very good. So let's go back to this satellite view. So I want to be very careful to not undermine the use of satellite observations too much. And so remember, there are areas here where it's obvious that we need to reduce emissions or take on policies that would mitigate what we're seeing from space. But I will tell you that even in the US, it's very unlikely that satellite observations will lead to specific decisions. And so, for instance, if you're looking at NO2 observations from space, what you don't have is what we call source apportionment. So if you look at NO2 and formaldehyde from space, you can see that things are poor, but it's very hard from spaceborne observations to attribute where the emissions are coming from. And that's where the ground level becomes very important. So in terms of this information, I think it's very important for satellite information to lead to commitment and to notice areas where action is needed. But then the actions really have to ultimately be based on real information on the ground. If I want to reduce NO2 in my location, what is the major source of NO2 and how would I need to change it? If I want to reduce hydrocarbon emissions, what industries and what activities are contributing the most, and how is that affecting my location? And so I think that in terms of awareness and in terms of pressure to act, satellite data can be quite valuable. But in terms of defining specific actions, the ground observations really have to come into play at that point. And so, again, bringing ground observations into play in Pakistan would be very powerful in terms of trying to really demonstrate what changes you want to make and how they would benefit air quality. Does that help?
Yes, I got it. Thank you so much.
Okay. Thank you.
Let's move to another question from Mr. Iftikhar.
Hello, I'm sorry for not turning on my video because I'm sitting in an unlit room because of load shedding. I would like to thank Dr. Crawford for his very detailed presentation. Actually, I want to build upon the discussion you had with Mr. Dejana. For Pakistan, we all know that due to lack of resources, maybe we cannot afford such high-tech technology, but what would be the starting point? What could be a very good starting point so that, for example, can we have some reliable models with some correction factors, for example, for the weather or some other factors which could be useful in this regard, so that we can have, we can move forward, or we can be at least helpful to provide you a reliable data. Thank you.
So, yeah, from my perspective, and I go back to this picture to show you, indeed, Pakistan is really not very, very well covered. There are a few monitors in Pakistan, but remember, what's being observed is PM 2.5 and PM 10, which is really the end result. And so, knowing that you have high aerosol pollution really doesn't address the question of why is the aerosol pollution there? What caused it? Where did it come from? And that's why I really believe that at a minimum, at least one well-placed research site, and Lahore would be a great candidate, that doesn't just look at the amount of PM 2.5, but looks at the composition of the aerosol. How much of it is nitrate versus sulfate versus organic material? How does NO2 and or formaldehyde vary through the day? I think investing in one site that really digs into details is a great start. There are, opportunities to look at the use of small sensors, but again, small sensors need to have an anchor, a place that's calibrated so that you can do comparisons to help understand them better. Because when used uncalibrated, they really can confuse things. And so, some combination of rigorous measurements in one or two locations and some small sensors could really help Pakistan, I think. And Fahim already knows this. He can talk to you in more detail about how those things might be compelling.
Yeah, thank you, James. Yes,
I
just want to share with Iftikhar and other audience that at NUST Islamabad, we have started buying the ground monitoring station. We do have similar kind of technology, but not like Pandora. We do have the MaxDOS. There was some kind of similar information, but not exactly how the Pandora is doing. We do have some satellite data as well here at NUST. So my student actually work on these things. Yeah, so if there's another question from any other audience, please raise your hand. James, if you're not, we are just on time. If you allow me, I have a very quick question for you.
Yeah.
Yeah. So I was just wondering, because what I have observed, that first thing is that, and it's just dilution factor with the advent of, with the evolution of boundary layer. So the NO2 is actually diluted and it's moving upward. And I was just wondering why this quantity of NO2 during.
Hang on just one second, Fahim. There's a jet flying over my house, so I'm starting to have trouble hearing.
No.
So yeah, we're talking about this dilution effect on things. Now go ahead.
Yeah, NO2 is just diluted because if you compare all these aircraft profiles from morning, then midday, and then afternoon.
Yes.
So it's just dilution factor, and the NO2 is just transported to the higher altitudes, which is just the rising of the boundary layer. And
that's correct.
I was just wondering why this is happening, because normally we know that NO2 is largely photolyzed, and particularly in the polluted layer. How to address that? The existing knowledge that we have, VOC limited regime and NOx limited regime. Then would it be okay? Would it be helpful if we also compare the ozone results? Then probably could be indication. But I also have seen similar behavior in formaldehyde over Seoul, that this was again the photolysis of formaldehyde itself wasn't there.
So you're saying you're not seeing those things at higher altitude?
Yeah. I mean, it was just dilution factor, rather chemistry wasn't there, photochemistry.
That is interesting. So I didn't show any ozone measurements, but we often show in our aircraft data that the ozone at the top of the boundary layer is greater than the ozone at the surface. And so it appears that the rate of ozone formation is greatest at the upper boundary layer. And so a lot of the ozone increase at the surface may be really due to transport downward of what's being produced above the ground. And so these aircraft profiles were really important because, you know, they really challenged the way that we saw the way the boundary layer behaved and what was happening in terms of the distribution. And in terms of the picture, they do corroborate the other points of view. So I do think that information is real, but I agree with you that it seems to change the way we view how the boundary layer pollution regime operates.
Yeah, and a very interesting point. I mean, it has started a new debate in the atmospheric chemistry business. Like, I mean, if we just take into account the satellite columns, that gives us some different story. I mean, it's total column, the emissions are confined. But because air quality indices are mainly based on the ground surfaces, so that might be misleading. Because at the time, satellites are giving us high NO2 or formaldehyde, but at the ground level, we don't see that. It's not.
That's right. That's right. Yes, that's the problem. And so without model interpretation and some other way to translate, you know, the satellite's still telling you the total amount of material present, but you're not seeing it at the ground level. So you know it's there. It's just not detectable from a ground measurement.
Yeah, again, the photochemistry is missing. So if satellite are giving the total column, it's still constant throughout the day. So that, well, satellite gives just one time, but that means something. The model should translate this fact that what's happening actually.
Because yes, and that's where
formaldehyde and NO2 is short-lived.
That's why I showed the model at the beginning of the talk, which is that the models are challenged by this. Models do not carry very rigorous boundary layer dynamics, and there's a lot of very non-realistic mixing going on. And so this is a real challenge for models to capture the boundary layer effects accurately. This is a real problem.
True, I agree. So it's going to be kind of new avenues of research and the challenge, definitely, as you mentioned.
But I emphasize that each one of the viewpoints is useful. They just by themselves don't really capture all the details.
True. So thank you, James, for sharing your insights about all the important measuring tools for air pollution with us. And I really appreciate your effort by spending time in the early morning at US. So as we are heading towards the night at US, it's the early morning time.
All right. Thank you. I was happy to join.
Really appreciate it.
Yeah, thank you very much for inviting me in.
Dr. James, if I request you to have a group photo in your presence, would that be okay?
To do what?
Group photo.
Sure.
Shall I? So if you can.
My camera's on, so.
Yeah, your camera is on. I would request the participant to switch on the camera as well. And if I request you to please stop sharing the screen so we can have.
Yep, let me do that.
All right, great. As we did before, this time we do it a little bit different. Last time we tried X. This time let's try 0. So we all make 0, right? The way it is like this one. I hope you all can.
You want me to do this?
Yeah.
Yes. It should be right straight to your forehead. All
Okay.
right, great. So please switch on the camera. We'll take it 2-3 seconds. So Shanila is here, I guess. Yes, she will be taking the photo.
Yep, I'm
Switching.
here.
Yes. All right. So
Yep.
we
On count three.
all camera.
1, 2, 3.
Wait. We just try to. All the camera should be on. All right. Okay.
Ali, can you please take it on your side as well because my internet is breaking. I
Okay.
feel
I'll
my
try to.
internet is breaking.
Oh no, no problem, no
Yeah.
problem. I'll try to do it
I
as
have
well.
taken one, but I'm not sure.
Okay. So you're all ready. Okay. So let's
Here
go.
we go.
And 3. Awesome. Awesome, guys.
Thank you. Thank you.
All right. Thank you, Dr. James. Thank you, everyone. Thank you so much. Thank you, Dr. James, for your time.
All right. Thanks. I'm going to have to go to another meeting, but I enjoyed it. Thanks for having me.
Thank you. Thank you.
All right.
All right. All right. Welcome back, everyone, to the session. Before we start next session, I would request Dr. Fahim, with your permission, we'll take a 5 minutes break just to relax and do our thing. Like if you have
It depends if the audience actually wants, then we can take a break. Otherwise, we can go for this is the last speaker of the day.
The last speaker, I will just request for 5 minutes. What do you guys think? Should we take a 5 minutes break?
Dr. Fahim, Muhammad Ali knows us better, so we need 5 minutes break.
Okay. I totally second you. And so we will take a break. So.